Hello everyone. In this video, we will be discussing about designing of flange couplings, bushpin couplings, and muff couplings. So first, we will see the design of the muff or the sleeve coupling, where we can able to see this all these dimensions. Where small d is nothing but diameter of the shaft, capital D is nothing but diameter of the sleeve or muff, and L is nothing but the length of sleeve or muff. And when we speak about specifically for the key, we have small l, that is length of key, small w, width of key, and small t, thickness of the key. So design of the muffler sleeve coupling. First thing is, first step is design of the shaft under torsion. So the formula to be followed to study, that is T is equal to pi by 16 into Q into D cube. And the design of the sleeve, from this we will be finding out D value, because Q value will be known and D value will be known. So diameter of the rod or diameter of the shaft will be finding out from this step. Then afterwards we will be finding out capital D value and L value from second step, that is a design of sleeve or a muff under torsion. So the formula is pi by 16 into Q into capital D cube into 1 minus K power 4, where K is nothing but a small d by capital D. So even this formula is available in the data handbook, that is K formula, D formula, and L formula. So where D is nothing but 2D plus 13, because already we will be knowing the small d value. So from this we will be finding out capital D value. So once it is done means, we will be finding out the length of the sleeve by using the formula 3.5 into small d, that is diameter of the shaft. So and from this we will be cross checking the dimension of the sleeve or the muff for the torsional shear stress. And next thing is, next step is the design of the key under torsional shear. So we will be finding out the like the thickness, width, and other things by using this formula, that is T is equal to F into D by 2, which is equal to uh, uh, L into W into Q into D by 2. So by we will be checking the dimension of the key for the torsional shear stress. And next thing is the design of the key under crushing stress. So T is equal to F into D by 2, which is equal to L into D by 2 into crushing stress into D by 2, where W is equal to D by 4. So T is equal to 2W by 3, which is equal to D by 6, and L is equal to capital L by 2, which is equal to 3.5 D by 2. So we'll be checking the dimension for the key for the crushing stress. Then moving to the second type, design of an unprotective flange coupling. We can able to see this the side view and the front view, where two flanges has been coupled together with the help of a key, and this is a driven shaft, this is a driving shaft, where the shaft dimensions are different. And even in this view we can able to see the key, the shaft projections, and even the bolts and screws which they have used, that also we can able to see in this particular sketch. So here this is a unprotected. This is an unprotective flange coupling, and this is a protective flange coupling. So what is the difference between unprotective and protective? We can able to see this. We can able to see this, where in unprotective both upper side and like lower side it is looking very similar, but in case of the protective flange coupling, it is different. So in the bottom side only it is completely covered with these kind of things, but in the bottom, in the lower upper side, it is completely made with these kind of setup, but in the lower side it is made with a few technical alterations, where small d is nothing but diameter of the shaft, and capital D is nothing but diameter of the hub. You can able to see this, and the formula is 2D, and D1 is nothing but a pitch circle diameter of the fasteners, that is 3D, and capital D2 is nothing but a diameter of the flange, that is 4D, and small d1, you can able to see this. This is nothing but a core diameter of the bolts, and the capital L is nothing but length of the hub, which is 1.5 times of diameter of the shaft, and W is nothing but the width of the key, and T is nothing but thickness of the key, and L is nothing but length of the key. So all these things we can able to find out the formula. For W it is D by 4, and for the thickness it is D by 6, and for the length it is capital L. And we have TP, we can able to TP and TF, where TP is nothing but thickness of protective circumferential flange. The formula is 0.52D, and TF is nothing but thickness of the flange, that is half of the shaft diameter. And then is nothing but number of bolts which we are using. You can able to see in this sketches where the number of bolts is mentioned. So first we will see the design procedure for the flange coupling. First one is we will have to find out the diameter of the shaft, which is very important. So by using the design of the shaft and the torsion formula, that is T is equal to pi by 16 into Q into D cube, where Q value and T value is known. From this diameter we will be finding out. Once the diameter is calculated, we will be checking the standard diameter from the table 14.4 from the 14th chapter design data handbook. And after finding out the standard diameter, we will be finding out the hub diameter, that is capital D, by using the formula capital T equal to pi by 16 into Q into D cube into 1 minus K power 4, where K is equal to D by D, that is small d by capital D. And already we know one more relationship, that is small capital D equal to 2D and capital E equal to 1.5D. So using this empirical equations, we will be checking the dimensions of the hub for the torsional shear stress. And next is design of the key under torsional shear, that is T is equal to F into D by 2, that is T into W into Q into D by 2. So using these equations, we will be checking the dimensions of the key for the torsional shear stress. Next one is the design of the key under the crushing stress. Like how for the under torsional we check, even under crushing also we will be checking out, where T is equal to F into D by 2. So L into D by 2 into crushing stress into D by 2. So from this W and T and L will be finding out, where W is nothing but D by 4, T is nothing but D by 6, and L is nothing but length. So using these empirical equations, we will be checking the dimensions of the key for the crushing stresses. And next one is design of the flange under crushing stresses. So the formula is T is equal to pi D into TF into QF into D by 2, and from this the TF is nothing but D by 2. So again, by using this formula, we will be checking the flange dimension for the shear stress. And next is bolt under torsion. So the load on each bolt is Fb is equal to pi by 4 into dc square into qb, and the load on all bolts is Fb is equal to n into pi by 4 into dc square into qb, where n is nothing but number of bolts. So consider 3 bolts for small d up to 40 mm and 4 bolts for d up to 100 mm and 6 bolts for d up to 180 mm. So the torque transmitted by the bolt is T is equal to n into pi by 4 into dc square into qb into d1 by 2, and capital D1 is equal to 3d. Then moving to the next one, design of bushed pin type of flexible couplings, where we will be having a rubber bush of thickness approximately 6 mm, because usually that is recommended. So that is why this particular coupling is called as a bushed pin type, and why it is also called as a flexible one, because this kind of couplings will be having little flexibility, some angular relaxation will be there, and apart from that, D, small d, capital D1, D2, everything remains same. So we can just see this. The very first formula, we will be finding out diameter of the shaft by using the torsion formula, that is pi by 16 into q into d cube. In case the torque is not known, then from the power equation we can able to find out, that is 2 pi nt by 60. Then next we will be finding out design of the pin, that is the bush thing. So that is formula is d1 equal to 0.5d divided by square root of n. Here the n should be the number of pins assumed depending on the number of bolts. The calculated diameter of the pin from the above equation, d1 is modified to d2 by applying the brass bush of thickness 2 mm and rubber bush of thickness 6 mm. The diameter of the rubber bush D2 is equal to D1 plus 2 into thickness of brass bush plus 2 into thickness of rubber bush, where D2 is equal to D1 plus 2 into 2 plus 2 into 6, so which is equal to D1 plus 16. So pitch circle diameter is D1 is equal to 2 into D plus D2 plus 2 into number of pins, so 2 into D plus D2 plus 2 into N. So the pin may fails under bearing pressure, that is PB is equal to F divided by L into D2, and F is equal to L into D2 into PB, and F is equal to N into L into D2 into PB, and T is equal to F into D1 by 2, and finally T will be getting N into length into D2 into PB into D1 by 2. And this is the design of a bushed pin type of flexible couplings, where the maximum principal shear stress formula and maximum principal normal stress formula we have to take, and finally the shear stress induced the formula we have to find out. So the formula will be getting out from equating these two, will be getting F divided by pi by 4 into D1 square, and section modulus formula, bending moment formula, bending stress formula is already known. So the design of the hub under torsion, K is equal to D by D, D equal to 2D, and L is equal to 1.5D. And the key under torsional shear stress and key under crushing stress, the same formula what we discussed in the previous case, same we will be using. And finally, the design of the flange, that is the thickness of the flange, will be finding out by the relation 0.5D. So with this, I'll be winding up with this video. and the numericals of these couplings will be discussing in the upcoming